Today we're going to talk about training a small language model. We're going to cover everything you need to know in a non-PhD style, so it's accessible for everyone. And we're actually going to cover 3 different types of language models. So let's get started. For the agenda today, we're going to do Language Models 101. This will be a crash course where it doesn't require having a PhD to understand. Next, we'll discuss building a GPT-style language model, and we're also going to demo that model at the end of this section. Then we're going to cover fine-tuning and optionally quantizing. If you're looking to build a small language model, this is actually the recommended way of doing it. We're also going to have a brief discussion on the various types of language models and even include a demo of one in particular. So I thought it would be good to start with a primer on language models in general. This will give you an introduction to some of the terms that are commonly used and also how those terms and processes translate into building and training a language model. So what is a small language model? A small language model is actually very similar process-wise to a large language model. Language models process text input, understand context, and generate natural language content. So if you've ever used anything like ChatGPT, Claude, or Gemini, those are very massive large language models. You ask a question, it generates an answer based on the context of that particular question. Language models predict words or tokens that come next in an answer. Where small language models is a subset of models that require fewer resources to run, you can run these small language models on modest or inexpensive GPUs and quite possibly even CPUs. There are a number of CPUs out there that have extensions in order to accelerate floating point calculations specifically designed to run AI models. At the end of the day, the intent of using a small language model is to require fewer resources to run, which also cuts down on infrastructure costs, power, and cooling. So our first part of our discussion, we're going to create a nanoGPT-style causal language model. When you build out any kind of model, whether it's a full-blown language model, a small language model, or even a traditional machine learning model, the process really encompasses 4 steps, which we're going to cover in more detail in the next few slides. You typically start with data preparation. In this step, you collect and prepare the data for model training. Next, you tokenize the prepared data and convert the text into inputs. Then you train over the data. There's training loops iterating over the training data over many epochs or steps. This then finally outputs the model for inference. What is a nanoGPT-style causal language model, and what does the architecture look like? Here's a blueprint for the terms and processes you need to know to understand what GPT-based models do. First, text is converted into token IDs. We call this the vocabulary. Depending on the saved model format, you'll often see a vocabulary file accompanying your model. Each token ID becomes a vector. In order to transition from one token to the next, we need to vectorize it. Depending on the model, you have tens of thousands of different paths to transition to the next node. You might hear this word called attention. When talking about large language models and how they operate, attention is the ability for language models to consider past context for semantic nuance. For example, we have the 2 sentences, swing the bat and the bat flew at night. The same word exists in both sentences, but the word bat has very different meanings based on the context of each sentence. The next term you've probably heard of is transformer, as in generative pre-trained transformer. What a transformer means is a neural network architecture or representation that handles sequences of tokens in parallel using attention or context for building out relationships. The next term or step in the process is using prediction head to take all of those things that came before it and create a score. The most probable one determines what the next token should be. Finally, we have the autoregressive loop. Take the entire context or attention of tokens, transform them, or in parallel use these threads of understanding to predict the next token via the prediction head, and generate the next token. You loop and do this over and over again until we have our generated answer. Fundamentally, using data science terms, this is how a large language model works. For a small language model, it's effectively the same thing. The differences are, we have a much lower parameter count. So instead of trillions or hundreds of billions of parameters, you might just have hundreds to about 10 billion parameters instead. Small language models tend to have smaller context windows. That is the amount of tokens the language model can process in a given conversation. And the vector dimensionality or reasoning capacity might be reduced. With every AI or ML problem, it always starts with the dataset. even for small language models, you're going to need a ton of data. I considered a couple options when picking out the data set. The first one was Tiny Stories, which sits at 1.6 gigabytes, which is a very small, clean data set that is story-based. The second one is what we ended up using in the demo, called FineWeb-EDU, which is 10.4 terabytes. I picked this one specifically for the attached white paper found at the green link at the center of the slide. This is a great paper that described the time and effort and process it took to curating this dataset and train the model. Like any dataset, we generally have to break the data into 3 parts. There's typically training data, validation data, and test data. So think of the training data as being used to update the weights. The non-data science way of describing the training data is practice or memorization for learning patterns. Validation data is for honing better answers. Think of this as a coach providing you feedback to get better answers. Test data is to see how well we did for the final exam, so to speak. The gauge to see how the model is going to perform given real-world data. So now that we have our data set, we have to transform the text into something that our training process can use. For that, we use a tokenizer. There are many different types of tokenizers. You can break the words into smaller chunks, like groups or letters, via byte pair encoding. It can also be a whole word, like in WordPiece. There's even sentence piece, which is actually kind of a misnomer. It technically isn't a tokenizer in the traditional sense. It extracts tokens from chunks or phrases from a predefined list. Once the tokens are extracted, they are assigned a unique number, and those numbers represent the alphabet or vocabulary. Each tokenizer will have their own different meaning for assigned numbers to tokens. Probably the most important thing to understand about tokenizers is if you tokenize a dataset using one particular tokenizer, you can't use a different tokenizer mid-process. Think of a tokenizer as an encoding. If you change the encoding, you change the language. A great example of this is if you were to encode something like a document using UTF-8, and if you use a Unicode parser to parse the document, that document would appear corrupted, and the same is true for tokenizers and language models. So when you train a large language model, or even a machine learning model in general, the training process is still the same. As you start ingesting training data, you compare it to the validation data. That comparison is what the learning framework needs in order to make necessary adjustments to get closer to the truth. It's a very high-level, non-technical way of understanding how the process works. During this process, the model is scored. The process keeps refining and adjusting and comparing until you get the lowest score possible. Then you save the model in a certain format, in our case, safe tensor PyTorch checkpoints, because it's cross-platform. Here are some other terms you should be familiar with when it comes to training models. You might hear the term loss function, and that's just simply an evaluation between a fact and the answer. It measures how off or far from the truth you are, which means the lower the score, the better. The last term you might hear is perplexity, and I'm not talking about the company, I'm talking about the concept, which defines how wrong is this model on average. When we move to inference, we're literally building a next token prediction engine. We're using attention, or the previous tokens that came before it, in order to predict the next one. This is what a causal language model is. We are only ever looking one token ahead. In this language model training process, what we're really doing is establishing patterns at multiple scales and levels for training data that we're supplying. This could be fragments of a word, punctuation, individual words themselves, phrases or groupings of word, the order of tokens, and even how the words are structured. Based on all that information and patterns in the training process, we generate output based on ranked lists of likely next tokens using the attention head. It also turns out you have the ability to tweak or tune the process using various knobs. This is where you start to see things like top K and top P, and all of those things that allow you to increase the variability for the next token selection. So to go over the process one more time, you take text, turn them into token IDs. You take these tokens and vectorize them. These are how you transition from one concept to the next. We have the attention mechanism, where we consider the tokens that came before it. We have the transformer layer, which takes that history and is used to predict the next token at scale and parallel. We have multiple prediction heads, which we want to keep as many different multiple parallel trains of thought going. The best answer is evaluated, and we run through this autoregressive loop appending one token after the next. And if you try to run this process as a simple machine learning training process, you're likely to get a crash in your training process almost instantly. It turns out training a language model is actually quite complex due to the nature of the problem. This is exactly what that failure might look like. If you naively try to treat even a small language model training process as a machine learning model, you quickly realize the amount of data required in order to train a small language model is too large. In fact, it's so large that you will even run out of memory on an H100. So now let's talk about how to take what we've learned and do it the right way, the way that will actually work, where you'll be able to train a small language model from scratch. So the first thing, a single H100 is not enough. I did this just as an experiment to see how far it would get. It turns out this is super comical because you won't even get past the starting line. You instantly fill up your memory and you crash out within the first minute. So if a single H100 or H200 is not enough, then we need to expand into multiple nodes. In my experiment, I switched to a single node with 8 H100s. As you can imagine, this gets pretty expensive, even for a conference talk, when you're talking about roughly $24 to $28 per hour. So for the demo at the end of this section, we're actually going to quit quite early in the training process, or roughly only about 10% of the way through. And because we're stopping early, that model is going to be not so great, actually quite bad in fact. Even with 8 H100s in a given node, the FineWeb EDU dataset is still far too large. You can't fit everything into memory and even distribute into multiple GPUs, so static loading will not work. When you have datasets this large, you need to switch to a streaming interface. We need to stream the dataset as you need it, and one very popular method is using the streaming token dataset interface on Hugging Face. It's a pretty good library, and if you can do things like deterministic split on the dataset, and you can shuffle the input while you stream. Additionally, if you're interested in data management, increasing the speed and throughput for streaming for your datasets to GPUs, NetApp has a wide variety of solutions and storage offerings that play wonderfully in this ecosystem. The other thing to note is when you train a machine learning model, you have this concept of training loops or epochs. The number of epochs represents the number of complete passes over the training data. In this particular case, we have to use a step-based training system since we can't load the entire dataset into memory. And in this step-based training, we're actually processing chunks of data in batches dynamically. Since we're changing our training process to accommodate a language model, we're going to use an established tokenizer called tick token, which is actually based on OpenAI's GPT-2 byte pair-based encoding. Then we're going to use GPT-config, which captures the configuration parameters used to train a GPT-2-style language model. This config defines things like the block size, the number of layers which capture the number of transformer blocks, the number of attention heads, the vector dimensionality for each token ID. Finally, when you combine all of these things, use the FineWeb EDU 10 terabyte dataset, you'll roughly get a 1.8 billion parameter model. If you're interested in watching this demo, I would invite you to click the link in the slide here to view this on YouTube. So based on the demo, even with all of that resource, a good data set, and the process to build out a small language model, you're still looking at roughly a GPT-2 equivalent language model, which in this day and age is not that great. Now, keep in mind we cut the training process short, and that has dramatically impacted the quality of the model we generated. But if you remember the white paper in the green link, if you were to continue training this model to the end, it would require about 6,000 GPU hours on an H100. If you do the math on that using a single node with 8 H100s at roughly $24 an hour, you'll get a cost of roughly $20,000, which yields about an 8 billion parameter model. Just understanding those numbers, you can see that very few people in reality will actually do this. You need the hardware, power, cooling in a data center, and you're still talking about the capital in order to train even just a GPT-2 type model. Now imagine trying to train the latest Claude 4.6 or GPT 5.2. So I've given you the explanation of what a training process looks like for a small language model from scratch, but you don't need to have a PhD version. If you want to understand this in much greater detail with the PhD requirements, Andre Kaparthy, who is famous in the AI space, has a 2-hour video on how to train a large language model from scratch. So if very few people are going to train a language model or even a small language model from scratch, how do you create specialized models based on your business rules, data, or ideas? This is where fine-tuning steps in. You can fine-tune an existing language model and then optionally quantize it if you want to reduce the number of resources, whether it's GPU or memory, in order to run inference. So what is fine-tuning? Fine-tuning is the process of imparting knowledge directly into the weights of an existing language model. You start with a language model that's conducive to your goals. This language model tends to be a generalist type model. Then you have training data, which is used to specialize that model for one specific type of job. What you're effectively doing is creating a subject matter expert. You're imparting more data and information into the weights of that particular model, so it's better able to answer those particular questions in that subject or domain. The training process at a high level is roughly the same. What you're ultimately doing is trying to change the model's purpose or behavior. This is the key takeaway in fine-tuning. So, a non-data science way of thinking about it, I like to use the analogy like creating a fork on a project in GitHub, then creating a feature branch that massively changes the purpose of a particular project geared towards one purpose. So after you fine-tune the model, you optionally have the ability to quantize the model. So what does quantization do? It allows you to use a simpler mathematical representation that's more conducive to a budget GPU or even a CPU. By using smaller or different numeric representation, which translates into smaller byte requirements, this simplifies the computational resource required as well as the memory capacity needed to load models into memory. Because you're making the math easier for a GPU or CPU, the inference is faster, and memory requirements are a lot lower. When you quantize a model, what doesn't change? Well, the things that don't change are the context window size, the attention heads, and the number of transformer layers. Those things all stay the same when you take a model and run it through the quantization process. There are 3 different methods for quantizing a model. The first is quantization-aware training. The model is trained or fine-tuned with a fake quantization module to simulate low precision during training. Weights and activations are quantized in the forward pass, allowing the model to adjust quantization errors. Static or post-training quantization. Both weights and activations are quantized to lower precision. A calibration dataset is used post-training to determine quantization parameters for each layer. Finally, dynamic quantization. Weights are converted into lower precision, int 8 or float 16, while activations remain in high precision. They are quantized on the fly during inference. So what this looks like graphically, before quantization, you have a higher memory footprint. You have higher processing requirements in the form of a GPU. Inference speed is likely faster because of that GPU. But the correctness and reasoning is really, really good. The reason why you're picking this type of solution is because you have a GPU in order to assist with all the computation and have a much larger knowledge base for your model. After quantization, you're decreasing the memory footprint required. You are decreasing the processing power where you only need a lower end GPU or even a CPU. Inference speed is increasing because you don't have the assist from the GPU. And the correctness might take a small hit depending on the quantization format. What things are getting reduced or removed from the model during this process. So for review, this is what a mental map of fine-tuning workflow looks like. Start with the pre-existing or pre-trained large language model. Start with the pre-existing or pre-trained small language model. You do dataset preparation. Using the dataset, you change the weights of the given model to impart specialization into that model. There's typically an evaluation step. Then you deploy your subject matter expert or your fine-tuned model for inference. For our demo, we're going to train a SQL-based small language model. We're going to start with Qwen 2.5, 7 billion parameters. The dataset we're going to provide is the synthetic text-to-SQL dataset. This dataset format contains a SQL schema plus a question and the resulting SQL statement. The fine-tuned strategy we're going to use is LoRA, which augments the weights and attention projections based on the SQL dataset that we're using. Next, we're going to quantize from floating point 32 to int 8, so using a fourth the number of bytes used for representation between these two number sets, and obviously a much friendlier compute mechanism for CPUs. Finally, we're going to use a typical Hugging Face chat template to take our user input and parse output. If you're interested in watching this demo, I would invite you to click the link in the slide here to view this on YouTube. So we created a specific purpose-built small language model that understands SQL statements. The thing to note here, that it's much cheaper to perform this type of training. You're talking about hundreds of dollars versus tens of thousands of dollars. You do that by leveraging an existing small language model as a base and then teaching it that specialization. Optionally, you quantize that model, which makes it much more memory, CPU, or GPU efficient, which translates into less hardware resources in order to run the model. The other cool or interesting consequence of performing this type of small language model training, because you're starting with a base model, this approach is iterative. If you have new additional data as a part of your dataset, maybe it's a new version of SQL with new language definitions, it's much more cost effective to train this model in this fashion versus spending the tens of thousands of dollars training a small language model from scratch. I thought it was worth to discuss that there are many types of different language models beyond the typical Q&A model like Claude or ChatGPT. We're going to discuss a few of them and actually demonstrate one of them today. So most of us interact with large language models like ChatGPT, Claude, or Gemini. These are typical Q&A chatbots. Ask it a question and it provides an answer. But there are many different types of language models. You've probably used some of them like summarization, code generation. Others include classifiers like named entity recognition, performing semantic search. And for our demo, we're going to demo a masked language model. Suffice it to say, there are many different kinds of language models, and it all requires some input, some training, and in order to get some sort of achieved output. So for our example and what we're going to demo, it's a masked language model. So what does a masked language model do? This model fills in the blanks. If you've ever played the word game Mad Libs, this is exactly what this model does, but it predicts the most likely word to fill in that spot. So for our example sentence, the LBC stands for long blank California. If you pass this sentence through a masked language model, it would come up with beach, as in Long Beach, which is where I'm from. A masked language model works by reading the whole sentence, looks at the blank space, and predicts the value. You have the things like top P and top K to adjust your output. You might be asking yourself, what are you going to do with this masked language model? What can it be used for? And it's actually a surprising great number of things. You can extract file names or IDs, you can perform classification or routing, and believe it or not, you can even use it for search. If you're interested in watching this demo, I would invite you to click the link in the slide here to view this on YouTube. So let's talk about the resources, code, and more for this presentation. All of the code for this session can be found in the GitHub link here. This presentation was originally given at the Southern California Linux Expo, hence the name for the link. If you're interested in learning more about small language models and quantization, there's an interesting blog post titled Less Compute, More Impact, which discusses why in the coming year we're going to care a lot about efficiency for our language models. As I mentioned earlier, NetApp has a number of product and solution offerings to help with dataset management, high throughput S3 streaming for training language models, machine learning models, and even performing fine-tuning. Some things to look into would be like Amazon FSx for NetApp ONTAP and NetApp Storage Grid. I hope you enjoyed this presentation. Thanks for watching.